Don't worry, that's not your actual pager going off. This was an experience I had about 5 years ago now. I was working for a startup in the cybersecurity space, and the company I worked for, they used to send out fake phishing emails. So a company could come along, they could sign up, and we'd send fake phishing emails to all of their employees, and we'd track who clicked the email as a way of training people on how to spot phishing emails. And my pager went off, I went to have a look, and there was an exponential number of emails being sent by the system. More emails were being sent than we could possibly expect. And I had two challenges at this point. The first challenge, I had no way to actually see what was going on inside the system. I had no observability into what the system was doing. The second problem, and the problem that was more personal to me, was that earlier that day I'd just made a change to the way the email sending behavior worked. I'd actually just learned about event-driven architecture at that time as well, and as these things go, when you learn about a new technology, obviously everything immediately needs to use that new technology that you just learned about. So I just refactored the way that the email sending worked. Now there was a scheduler service that would look to see when an email needed to be sent, and it would raise an email ready to send event. The email service would consume that email ready to send event, it would go off and it would send the email, and then it would publish an email sent event. The email sent event would then of course be consumed by the scheduler service, and the scheduler service would mark the record in the database as being sent, which sounds simple enough, right? You've got systems publishing events, you've got systems subscribing to events, it all seems nice and easy. The problem was I just changed the schema of that email sent event, which means when that event came back, there was no way to map that to the record in the database, which meant the record never got marked as sent in the database, which meant the email ready to send event got published again, and the process repeats itself, which is obviously not ideal when you're trying to train people to spot fake phishing emails and they receive 200 emails from Domino's. And this is one of the challenges with event-driven architecture, right? They seem like at the outset they're really easy, they're really straightforward, you've got systems producing events, you've got systems subscribing to events, but actually, once you need to maintain a system, once you need to evolve a system, once you need to test the system and observe it, things get really quite difficult, actually. So in this talk, that's what you're going to learn about. You're going to walk out of here with some practical things you can do to better implement observability, to better implement testing in event-driven systems. I'm James Eastham. I'm a serverless developer advocate at Datadog. I'm a Microsoft MVP. I'm an AWS community builder. And if any of you have ever seen me talk before, or you've seen any of the stuff I do online, you'll probably know there's one thing I love talking about almost as much as event-driven architecture, and that is pizza. I was thrilled actually at lunch today that there was pizza for lunch, because pizza's amazing, isn't it? And throughout this talk, you're now all going to sit in the shoes of an SRE at Plant-Based Pizza, the country's #1 pizza delivery company. And you're going to be showing your development teams how they can better test and how they can better observe event-driven systems to help them, the end result, to build a more maintainable event-driven system. So before we get into that, let's just understand how the actual application works. And this is a real application, by the way. You can go on GitHub, you can go and deploy this. There's a QR code at the end that you can use to actually go and look at all of this. So what actually happens is a create order request comes in. That comes into the order processing service. The order service is going to publish an order confirmed event once the order is happy, the order is ready to go, which the kitchen service is then going to consume. Kitchen service is going to go off and it's going to actually go and prepare the order, it's going to do the things it needs to do, its internal business workflows, before eventually publishing an order prepared event, which is then consumed by the delivery service goes off and it delivers the order to the person. You'll notice that the order service is also consuming them order confirmed and order prepared events. That's so that really impatient people like me who sit there furiously refreshing their mobile app waiting for their pizza can get an up-to-date status on where exactly their pizza is up to. And if you're building an event-driven system today, how many of you are working on what you would call an event-driven system, just out of curiosity? Okay, a few hands, cool. So as you get started building event-driven systems, like I said, things seem easy. You've just got systems publishing events, systems consuming events, everything seems nice and straightforward. That is until something comes along that I'm sure every single person in this room will have dealt with in their careers, and that is change. The systems we build need to change. The economic environment changes, the features change, the number of users we have change, and that causes us to need to change our systems. And really, stable systems are systems that never need to change. Unfortunately, that's not a world we have a luxury of living in. So as you start to think about changing your system, a logical place to start is to look at how you would test that system. As you change it over time to make sure it still works, to still do it things it needs to do, is useful. And back when I was working at AWS, before I joined Datadog, I was at AWS for a few years, and I used to talk to a lot of people about event-driven architecture, and one of the #1 questions that came up was, how do I test an asynchronous system? How do I test an event-driven architecture? And that naturally led to the question of what types of tests should I write? And I realize this is an incredibly contentious topic. Do I write unit tests? Do I write integration tests? Do I write end-to-end tests? For the purposes of this talk, I want you to try and forget about the category of test, if you will, the semantics of what type of test it is. Instead, focus on what exactly is being tested. And as you start to think about that, as you start to think about why is it that we actually test the systems we build? And to ask a more fundamental question, and I want you all to take a couple of seconds to think about this, why exactly do you all build software? Why exactly are you all working in software? Just take a few seconds and just think about that and get some kind of answer in your head. And I tried to think about this for myself. I tried to think about this with people I know, and the first logical one that came to mind, because we all like money. Software development is a well-paid position. That's obviously sensible. This is clearly a bit of a silly one. It's a good reason to work in software, right? It's a well-paid industry. It's a well-paid thing to do. The second reason, and the one that I at least finds more impactful for me, is that I love building really complicated stuff. Really complicated stuff. Don't you feel really good when you build something and there's a million things going on? There's so many different services and microservices and events and all these things. And I actually find this diagram funny, because the first part of my career, I spent it working on SQL Server integration services, if anyone's familiar. Integration packages that would pull data together from lots and lots of different databases and make this distributed system appear like it was a coherent whole. I was the guy doing the midnight heroics. And even after doing that, I still spent the next part of my career putting cool databases and event buses in places where cool databases and event buses had no right to be. I'm sure has anyone else done that, just out of interest? Put something somewhere where it shouldn't have done? Yes, yeah, I'm back. Awesome. Okay, then first two are silly ones. One of the number one reasons that come up when I think about why I work in software, why I'm sure many of you work in software, where many of people I know who work in software, is that you want to impact people. Most of the software we build, if not all of the software we are building, we're building it to make someone's life easier, better, simpler. And frankly, if the software you're building doesn't do the job it needs to do, it doesn't solve the user need that you need to solve, then, well, what is the point? And if anyone caught the talk earlier, actually, from the folks at Tenable, they were talking about basing SLOs on user requirements. Base your SLOs on like user journeys and user things. And that's the same idea we can take to testing as well. And there was a really great talk at QCon London last year from Martin Thwaites. I'd really recommend going to check out this talk if you're interested in testing distributed systems and testing in general. And one of the core ideas in this talk is that actually, if you're writing tests and you've got hundreds and hundreds of tests that cover tens of classes and every single method on every single class is all covered by your tests, it doesn't actually matter if your system doesn't meet the requirements that it has. And Martin talks about this idea of requirements-based testing. Write your tests based on the requirement that your system has. And when you think about a synchronous system, this is probably quite easy for all of you to think about. Let's imagine the order service. You're working with the order team inside Plant-Based Pizza, and they need to test this order service. And one of the requirements that the order service has is that when a user can come along and they can create an order, people want to order a pizza, great. And then after that, they need to be able to get the status of that order. And I'm sure many of you at this point can think about how you would write a test that would do this, right? You would spin up an instance of your application, you would make the create post request, you would make the get request, and then you'd assert on the results of the get request, something like that. But remember, you're working on an event-driven system. This isn't the only requirement that your synchronous system, that your order service has. One of the other requirements of the order service is that you also need to notify other systems that things are happening in your system. In this case, an order created event. You want to notify other systems that there's a new order that's being created. And when these events get produced, they're typically being produced onto some kind of other thing, whether that be Kafka, whether that be Amazon Event Bridge, whether that be Azure Service Bus. These events are going somewhere else. So how do you assert on something in a test that is actually just being published to something and there maybe is something else at the other end of that pipe? Or equally, some systems you work on will be completely asynchronous in nature. There will be no synchronous endpoints exposed. The payment service inside Plant-Based Pizza takes a take payment command that the order service sends onto a queue. And the payment service is just working through this queue. At some time later, it's going to publish either a payment successful or a payment failed event. Here, you've got no synchronous endpoint that you can make a request to assert on. Here, you've just got events coming in, and then hopefully sometime later, an event coming out the other end. But you still need to make sure that this system is doing the thing that it needs to do, right? It's meeting the requirements, it's taking payments. Some of you have probably felt like this when you've started to try and think about these things. Things are starting to sound a little bit tricky now, aren't they? Maybe some of you are thinking, let's just go back to building monoliths and running them on Windows servers. That's so much simpler. Don't worry though, there's some patterns that can help you here. And I'm sure many of you, when you're writing tests for applications or you're working on tests, you're going to spin up some kind of instance of your application. In an ideal world, you'll want a completely isolated environment that you can run your tests against, which probably means you're going to spin up your application itself. You're going to spin up maybe some kind of persistence layer, your database, whatever database technology you're using, and you're going to spin up some kind of messaging layer, whatever messaging technology you're using. Maybe you're doing this in Docker Compose locally on your machine. Maybe you're doing this by deploying to a staging environment, but ideally you're going to have this isolated environment that you can run tests against. So when it comes to testing asynchronous systems, what I would always recommend people do is to spin up one additional component as part of this infrastructure, something I would call a test harness. This can be a completely generic component. There's nothing complicated here. All this harness is doing is behaving like a subscriber. It's behaving like a subscriber, and it's exposing an endpoint so that you can retrieve all the events that have been published in a given period of time. How this would actually work in a test. So you're still going to do the same thing. You're going to spin up all your infrastructure for testing. You're going to make that initial post request to create the order. And the order service is going to give you back an order number, and hopefully behind the scenes, it's going to publish that order created event onto whatever messaging technology you're using. And you've also spun up this test harness, which is subscribed to all of the events that the order service is publishing. So hopefully, if that event makes it to your messaging transport, that's going to then be consumed by the test harness. And in your test, you can make a GET request to that test harness and say, hey, give me all the events for order 1, 2, 3, 4, 6. And hopefully, in that case, you can assert that an order created event has made it through to the subscriber. At this point, you can also build in some kind of schema test to make sure that the schema of the event that you receive actually matches the schema that you expect, which is another really useful thing to do in event-driven architectures. Now, some of you are probably looking at that and thinking, James, that's going to lead to really flaky tests, isn't it? Because you're publishing these things onto a message channel, then you're going off and doing other work, and some point later, maybe that message gets delivered somewhere. So what I would always recommend if you're doing this is to build some kind of retry strategy into your tests. Apologies if you're not a .NET developer. This is just a simple while loop that's waiting, checking for any events that have been received, asserting on that, and then waiting for a period of time between each check, which then naturally leads to the question, how long should I wait between the checks? And you can base the amount of time you wait, again, on the SLO of your service. If you want to process orders inside 300 milliseconds, base this retry strategy on that amount of time. And then if the test fails, that may well be a flaky test, but, well, you're not meeting your SLO anyway, so that's okay. So that covers testing. You're hooking into the actual flow of events around your system. You're making sure that events actually get published. And if you're really going for it, you're adding some kind of contract tests as well to make sure that the schema of the event matches the schema that you expect. Which leads us on to observability. No matter how well you test the system, it is always going to go wrong at some point. You have the most tested system in the world. Users will always do things you don't expect. Your system's going to break in new and novel ways. And I like to define observability as the ability to ask questions of your system, questions that you didn't know you needed to ask in the first place. And this becomes a real challenge when you're building an event-driven system. It's challenging because cause and effect is incredibly hard to understand inside an event-driven system. You've got services publishing events, you've got services maybe consuming them events, maybe not. Understanding who's upstream of you, who's downstream of you becomes difficult. When you compare this to a synchronous system, of course, you've got the order service maybe calling the kitchen service directly. You can almost follow the bytes across the network, and you can see that these two systems have a real clear impact on each other. So this challenge with cause and effect, this challenge with understanding dependencies, makes distributed tracing the most important thing to think about when you're adding observability to your asynchronous systems. And just to settle on some terminology here, this is at the top level here, the end-to-end flow of a request is what would be called a trace. Inside a trace will typically be made up of lots and lots of different spans, and these spans can span multiple different back-end systems. You can propagate your trace context so you get this one long continuous trace through all of your different back-end systems. Now I know I said that distributed tracing is the most important thing to think about. To add a caveat to that's distributed tracing with lots and lots of context. Spans and traces allow you to add tags, then tags can allow context. That context is what will allow you to ask questions of your system. It's context that's the key part of modern observability. And I like to think of context in two different ways. The first way is technical context. Technical context is the thing that's common to all of the systems that all of you are building. The HTTP route, the HTTP method, the HTTP status code. And actually, OpenTelemetry publish a set of semantic conventions for messaging spans, which is just best practices between you and me. This defines a set of context that all spans related to messaging should have. And there's some really useful things in here. Things like the operation name. Are you sending a request? Are you receiving a message? Are you processing a message? Things like the messaging technology that you're using. Here, this is a span that's sending a message to SQS, and it's sending it to a queue called the order confirmed queue. And then down at the bottom, you've got the message version and the type of event. So adding all of this information to your spans related to messaging then allows you to start drawing really good insight at a macro level on exactly what your system is doing. You can go and have a look for a given service and see all of the spans that are tagged with send, group that by the type of event, and then you can see exactly the number of events that your service is publishing. Equally, you can ask the same question, but say, show me all of the spans that are an operation type of receive, grouped by event type, and then you can see how many events of a given type you're receiving. So adding this technical context to all of your spans allow you to start drawing insight from how your system is functioning. But like I said, this is only one half of the context that's important. The more important context to add to your event systems is business context that's specific to your specific use case, your specific domain. Things like the order number, the user ID, the user account number. This will allow you to then ask the questions of your system. Show me all of the telemetry related to order X. A company I used to work for, actually, we used to have this question in the PR template. Whenever you wanted to raise a PR and merge a change, you had to describe in the PR how you would know that specific piece of code has made it to production. More often than not, that was implemented using span tags. You would tag a span. If that span was then found when you made a query in your observability backend, you would know that your code is now in production. Now, one thing I always like to point out at this point is, please, people, although I said add lots of business context, don't be adding credit card numbers to your observability backend. That's not a sensible thing to do. I don't want all of your security teams calling me in 6 weeks' time and saying, hey, you told all my teams and now we're... So add lots of context, but obviously not too much context, so you don't add things that shouldn't be in there. Now, tracing is really useful, but tracing isn't actually a silver bullet. Tracing isn't going to solve all the problems, because if we look at this trace here, this is a trace for that order processing workflow that I just talked about, and you've got the actual initial API request right up in the top right, the little green boxes that you can see. And the initial API request finishes in 200, 300, maybe 400 milliseconds. Oh no, it's over a second. There we go. But then you've got this big, long, extra purple bit that's taking 10, 11 seconds, a disproportionate amount of time relative to the rest of the trace. And you're just propagating your trace into all of these downstream systems. And this is some kind of business process that's running. And many of you will be in situations like this where you've got some kind of long-running business process. You've got an event that happens, something happens, then you've got a process that might take days, it might take minutes, it might take hours, weeks, months, whatever. So actually in this scenario, if you're propagating your trace into your downstream systems, you end up with this really long, rather unhelpful trace, because actually the initial request completed in a second, but the overall trace is now showing as 10. So this can actually add a lot more complexity to your observability if you just propagate your trace context everywhere. Thankfully, there's an alternative approach here, and that is using span links. So instead of propagating your trace, instead you create a link between spans in different traces. This allows you to keep independent traces for independent bits of your system while still understanding cause and effect, by still understanding what spans are upstream of you and what spans were downstream of you. Which then begs the question, which is the right want to use? Do I use propagation or do I use span links? And the general rule of thumb I use for this is, if you're working inside a domain, inside a business context, propagate your trace. Because typically as a developer, you're going to be working on the kitchen service. You're going to be helping make the kitchen service more resilient. So it's helpful to understand everything the kitchen service is doing inside one trace. But once you start communicating between services, between domains, then it can be a good time to link. So you still have that understanding of cause and effect, but you don't have this challenge with really long, complicated traces. So that's talking a lot about the down in the weeds stuff, the individual traces, individual request flows. But what about metrics? What about high-level things we can use to understand how our system is performing? And when I say metrics here, I don't necessarily mean sending metrics themselves. You can equally infer a lot of these metrics from your trace data by aggregating your trace data. OpenTelemetry also publish a set of semantic conventions for metrics for messaging spans, which again is best practices between you and me. And this is some of them, and there's some in here that I've put in here that I've found really helpful in my career when it comes to building event-driven systems. The first of those is queue depth. How many events, how many messages are they backed up in a queue? This can show you that your system can't deal with the throughput, or if this was a dead letter queue, this could show you that you've got a lot of errors in your system, something's going wrong. Then you've got the number of messages processed and the size, the average size of the message that's being processed. Now this can be useful both to understand throughputs, but also understand if you've got a sudden spike in the size of the message or a sudden big drop-off in the spike of a message, well, in the size of a message, should I say, that can indicate that there's been a change in the schema of the event, which means there's probably something that you're going to need to do somewhere. You've got the message age. This is the age of the last message that you processed. This can, again, combined with the queue depth, help you understand if you're dealing with the throughput that the upstream systems are sending your way. You've got the in-flight latency. How much latency is your chosen messaging technology adding to the overall system flow? If you care about latency, obviously this an end-to-end latency, this can be a really useful one to have. And then finally, you've got some kind of obvious ones like the number of errors and the number of the count of a type of each message, should I say. Now, which of these you choose to alert on is, well, completely up to you in your business case. If you care about end-to-end latency, then maybe message age and in-flight latency are the metrics you might care about. If you care about resilience and making sure nothing ever goes wrong, then that might be error count and the size of your dead letter queue, for example. And another important thing to remember when it comes to metrics and alerting is that success is a really important metric. If during the day you're processing an average of, 10 messages per second, and then all of a sudden you're processing 0 messages per second, that can indicate there's a problem somewhere. That might not necessarily be a failure, there might not necessarily be an error, but the fact you're not processing as many successful messages as you typically would be can be an indication that there's a problem. So remember, success is an important metric. Now, I realise that you're not actually all developers at Plant-Based Pizza, as much as it would be wonderful to work for a pizza restaurant and get free pizza every day. That's not a luxury we all have. So what does this mean for all of you as you're going back to your companies and you're going to help your teams implement better reliability and event-driven systems, or maybe you're building them yourself? So the first thing is, remember, when you're thinking about testing, is to test for requirements. The semantics of, are you writing unit tests, are you writing end-to-end tests, are you writing integration tests, whilst useful, fundamentally your software needs to do the thing it's supposed to do. If it's not, then it's not really that useful. So think about when you're writing your tests, think about, are you testing for all the requirements? And failure can also be a requirement. Imagine the payment service will probably want to write a test to say, if I receive the same event, the 4 events for the same order, you're probably not going to want to charge the person 4 times, right? So testing the failure requirement there is that you only want to process a payment once if you receive the same event for the same order multiple times. So test for the requirements that your system has. And secondly, context is king. It's context that will add the value to your observability, whichever observability backend that you're using. Because once you add context, you can start to play detective when things go wrong. You can start to ask the questions of your system to better understand how your services are communicating, how your system's performing, and if your system is doing the work it needs to do. Now, if you're interested in event-driven architecture, I've got a course on the Dome Train platform that's from zero to hero event-driven architecture. It takes you from no knowledge right through to building a real event-driven system. You actually build plant-based pizza, the application we've talked about today. There's a QR code there in the bottom corner. This is a link to the slides. It's got the link to the GitHub repo, which has all this code on it. It's got a link to my YouTube channel where I've got a lot more content about event-driven architecture and things like that. And yeah, if you've got any questions, I'll take them now. Equally, I'll be around all day today and all day tomorrow if you want to come and grab me. So thank you all very much for listening.